this is the first of a series of application videos of first-order differential equations, because we finally have all the tools we need to solve some applications. And today's one is very physical, namely an object of mass 10 kilograms is dropped from a height of 300 meters. And the question is, what is the velocity of that object? So, as is usual, the first thing is to draw a picture of the situation. In fact, let me play some magic. So that's what we have here. So once again, a ball that is dropped from a height of 300 meters. And in order to figure out the velocity, of course, we first need to find an ODE, because the course is all about solving ODEs. So, step one, find the ODE. ODE, well, we do have a mention of mass, and we want to find a velocity. So one idea is to use Newton's second law, which is a very prominent law in physics that governs mass, acceleration, everything. So Newton's second law, which, by the way, is the only physical law I will require you to assume. Any other physical laws will be given to you. And Newton's second law says, may the force not be with you, but may the force be mass times acceleration. So F equals ma. So in particular, F, force, which depends on time, F of t equals, so mass is 10, so 10a of t, where F of t, F of t is the force acting on the object, force, and a of t, which is the same thing as the derivative of velocity, is the acceleration. And therefore, what we end up getting is just F of t equals 10 v prime of t, where v prime, or v is velocity. Of course, we're not done, because, okay, on the right-hand side, we have v prime. On the left-hand side, we would like some kind of v to appear. So in other words, what we have to do now is study f. So study of f. F. And here you have to think a little bit in terms of the physical situation. So we have our ball, kind of like this. And again, the ball is going down. So in particular, there are two forces that are in play here. One is the force pulling the ball down, which has to do with gravity. And the other one is a force sort of slowing the ball down, which is friction. And we just need to find formulas of those two. So two forces. Forces in play here. One, again, being the force that pulls the ball down, which is gravity. And gravity here is given by mass times gravitational constant. So m times g, mg, where m is, as usual, 10 kilograms. That's just the mass. And g is 9.8. Yes. meters per second squared, which is what's called the gravitational constant. Which makes sense because, well, the heavier the ball is, the faster it falls. And also, well, on the moon, for instance, with a different gravitational constant, the ball doesn't go down as fast as before. Okay, and you don't need to know the formula mg, that would be given to you. That's on the other one hand, and on the other hand, there is friction, which again, in this case, it's given by minus gamma v of t. And I explain why. Minus gamma v of t. Where minus, because friction points in the opposite direction of gravity. Okay. V, because the faster the ball moves, the more the force of friction. And then gamma, that's what's called the drag constant. So not RuPaul's Drag Race, but here like drag as in slowing down. Drag constant. So that the ball sachets away and stop. Okay, very good. And those are the two components we need. So what is the force in the end? F is just gravity plus friction, which is, again, mg minus gamma v of t. And that then becomes 9.8 times 10 minus 2 v of t. Forgot to mention, but here the drag constant is 2 kilograms per second. And in other words, we get 98 minus 2 v of t, which is the missing link that we needed, because if you remember in the above, we had f is 10 v prime of t, but also f is 98 minus 2 v of t. So f was 10 v prime of t. So in other words, we get 10 v prime of t is 98 minus 2 v of t. And last but not least, dividing by 10, we get our differential equation for v, which is v prime is 9.8 minus 0.2 v of t. C'est la vie of t. And as I said, the cool thing is we can actually solve this differential equation, which we'll do now. But I do want to say, if you look in the notes, I have done a qualitative analysis, which you're welcome to check out. Notes. But here, since we can actually solve the ODE, let's do that. Solve the ODE. And by the way, so this will be the only application example where I actually solve the ODE, because the technique will be the same for all the equations that we'll see. Because notice we have v prime of t plus 0.2 v of t equals 9.8, which is precisely of the integrating factors form. So of the form, okay, y prime plus ay equals f of t. So let's just use the integrating factors method. But I do want to mention, we can also use separation of variables, integrating factors. So here, not even e to the integral of p of t, just e to the at, which is e to the 0.2t. So what we end up getting is, once again, v prime of t plus 0.2 v of t equals 9.8, and this junk, we want to multiply by e to the 0.2t. To the 0.2t, and e to the 0.2t. And once again, the beautiful thing about integrating factors is that the left-hand side just becomes a derivative. So e to the 0.2t v of t prime equals 9.8 e to the 0.2t. So we can just solve this by integrating e to the 0.2t v of t is integral of 9.8 e to the 0.2t dt. And then if you differentiate e to the 0.2t, a 0.2 comes out. So for anti-differentiating, you divide e to the 0.2t plus c. And we get e to the 0.2t v of t. Well, dividing by 0.2 is like multiplying by 5. So this becomes 49 e to the 0.2t plus c. And then if you divide all sides by e to the 0.2t, we get v of t is 49 plus c e to the minus 0.2t. Ta-da! We found the velocity of the object. And here's the cool thing. If you notice, as t goes to infinity, this term goes to 0. So in fact, what is the limiting velocity is just 49. No, as t goes to infinity, v of t goes to 49. And the cool thing is this limiting velocity doesn't depend on the initial condition. V of 0. So if you want sort of some qualitative pictures of what the solutions look like, well, here you have your 49, and the velocity either goes up or down, depending on what the initial condition is. And then using this, we can solve other cute problems that you can see in the notes. I mean, one thing you can do, of course, is to solve the ODE with some initial conditions, with v of 0 equals 0. And then in the notes, you'll find that v of t is 49 minus 49 e to the minus 0.2t. And it looks like that. You might start slow, but then it's just accelerating until it reaches 49. And then using the velocity and integrating, you can find a position. X of t, which is just integral v of t dt. And well, for the initial position, depending on your frame of reference, you can either use x of 0 is 0 or x of 0 equals 300. And then I think if you use x of 0 equals 0, you find actually find a nice formula. X of t is 49t plus 245 e of minus 0.2t minus 245. You can work out the algebra if you want. So what this looks like, kind of if you're putting your head upside down, it starts at 0 and kind of goes up, but like really goes down when you flip it. And then you can also solve cute problems like at what time does the ball hit the ground by solving x of t equals 300 in this case, and other very nice things as well.